Okay, what we want to do now is to take a look at the rest of Lab 2. So we're going to talk about the trapezoid tables problems and the paddleboat rental problem. And then we're going to try and look across those four tasks to learn something larger about growing patterns. We'll come to find that these are actually arithmetic sequences, something that you probably have seen in high school. Definitely going to connect to stuff you've done in Algebra 1, and we'll see how these things all kind of fall together as we look at these examples. So at this point, you've already turned in Lab 2, and so we're going to talk about the two tasks that I left for you to do on your own. We talked about the trapezoid table problem. You all worked on that. Mrs. Chen decided she would place the chairs around each table so that 2 chairs can fit on the long side of the trapezoid and 1 chair on every other side of the trapezoid. This way, 5 seats can fit around 1 table, and she found that 8 seats could fit around 2 tables. And I had asked you to figure out how many seats could fit around 3 tables, 4 tables, and up to 10 tables to generalize a rule and to connect your rule to the picture. So what I'd like to do next is just briefly look at this task, how I generated my t-chart, and then some of the patterns that we can see in that t-chart that help us look at recursive rules and then that closed formula and then connect it to the pictures that we're seeing in our trapezoid tables. When we look at the trapezoid table problem, we saw 2 examples, and again I'm going to generate my t-chart here with the number of tables and then the number of seats. And one of the things we realized from our picture is that when there's 1 trapezoid table there are 5 seats, and when there were 2 trapezoid tables there were 8 seats, and we can kind of see that. So if I draw my first trapezoid table, and I realize that the short side will have 1 and the long side will have 2, and then there's 1 seat here on each end, and you can see the 1, 2, 3, 4, 5 seats. And if I were to add another table, so now there'd be a long side here and then a short side here. One of the things I realize is that when I put this table here, this seat gets covered up. And what I'm actually going to do with this seat is I'm just going to move it to the end of the table. So it's now going to be here. I haven't added it, I've just moved it. But I am going to add some seats, and it turns out I'm going to add 1 on the short side and 2 on the long side there. And again, you can see I have 1, 2, 3, 4, 5, 6, 7, and 8. When I go to do my third table, again, it'll be a short side here, long side on the bottom. Again, I'm going to move that seat on the end just to the end of the table. I'm not going to add it or get rid of it. I'm just going to move it. And then I'll have 1 on the short side and 2 on the long side. So I will have added these 3 seats. So I should have, when there are 3 tables here, let's see, I should have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and indeed I do have 11. And I'm going to do a 4th table, so I'm going to put a long side here and a short side down there. Again, this seat, I'm not going to add it or subtract it, I'm just going to move it to the end. I'm going to put 2 seats here, I'm going to add a 3rd seat down here. Again, you can see this pattern that every time I add one of these tables, I'm really adding 3 seats every time. So when I have 4 seats, there are actually 4 tables, I will have 14 seats here. Okay? 1, 2, 3, 4, 5, 6 on the top, 7, 8, 9, 10, 11, 12 for the bottom, then 1 on this end and 1 on that end. You'll notice this end hasn't moved, and this one, even though I keep moving it, I'm not adding it or subtracting it. So when I look at my table, I can start to see this pattern that every time I add a table, the number of seats goes up by 3. every time I add a table, the number of seats goes up by 3. And again, in that triangle pattern, we can see those 3 tables that are added every time. And again, plus 3. So I can do this all the way out to 10 if I want to. I don't know how much room I'm going to have here, but I'll try 6. And it looks like I'm going to get to 7 here. But plus 3 will give me 17, will give me 20, and will give me 23. And then I'm going to go back and finish my table and think about how this recursive pattern, the one that's going down here, how we might use that to figure out our closed pattern with an in and an out. Well, those are horrible drawings. I'm going to try that again, maybe with a different color, to go from 5 to 17 or to go from 6 to 20. Didn't do much better that time, but hey. So that's what we're going to look at next. So after looking at our pictures and generating our table, we can kind of see, and I'm just going to put these all up here, and you can see that in this case I've generated my table with that plus 3 pattern we saw all the way up to 10 tables. Let me go back to that. So our closed formula, our recursive formula, our first next formula, as the number of tables increases by 1, right? The tables go up by 1 each time, 2 to 3, 3 to 4, 4 to 5. The number of seats goes up by 3 each time, and we saw that clearly in our pattern there. We actually saw that in our pictures as well. So there's that plus 3 that happens every time the tables go up 1, and that's what I used to generate to 7 in our other table, and then I've gone ahead and generated all the way up to 10, which is what the problem asked for. And now it's a matter of trying to figure out what our closed formula is. When I look across the table, I know that there's going to be some kind of multiplication and maybe there's going to be some kind of addition. So there's 2 operations that are going to happen here to get from 4 to 14, from 5 to 17, from 8 to 26. And one of the things we talked about before was trying to look at what happens if there were 0 tables and backing this up, because that will tell us what the additional constant is. So after we multiply, what are we going to add? So if I back up and think about 0 tables, and I subtract 3 as I do as I'm moving up, 14 minus 3, 11, 11 minus 3, 8, 8 minus 3, 5, and then 5 minus 3 would tell me that if there were no tables, that there would still be 2 seats. And if I know I'm going to multiply the number of tables by something, and then I'm going to add or subtract something, when there's 0 tables, that tells me at the end I'm just going to add 2. So 2 times what plus 2 gives me 8? Well, if I subtract this 2 and I work backwards to go from 8 to 2, 8 minus 2 is 6. 2 times what gives me 6? Well, that's going to be 3. Hey, this was plus 3, and it looks like if I multiply by 3, 6 times 3 is 18, and then I add 2, I'll get 20. And it turns out that our closed formula is so take the number of tables you have and multiply by 3 and then add 2. And if we think about our pictures, this is how many n groups of 3, where n is the number of tables. So if I have 6 tables, I know that in those tables I'm going to have, every table is going to have that triangle of seats that I add, and there's going to be 3 in there. So if I have 6 of those, there's 18. The 2 seats are the seats that are at the front of the table and then at the back of the table. And again, those are constant. They don't change, just like we saw in our picture. That's one of the reasons why it makes sense that we call this adding or subtracting at the end the constant. Okay, and the n is the variable. This is what changes. This is what stays the same. So those 2 seats, the one at the front and the one at the back, we're always counting those. And then it's just a matter of how many groups of 3 there are in the middle. So hopefully you got to these kinds of ideas as you were looking at the trapezoid tables for yourself. The second task you were to complete in Lab 2 was the paddleboat problem. And again, this is another one of those reverse pattern problems where I don't describe the relationship, but I just show you some of the chart, and from the chart you have to generate some more of the chart. And again, Susan is renting a paddle boat, it costs $1.50 to rent a life vest, and it is $6 an hour to rent the boat. Below is a table for the total cost of one person to use the paddle boat safely. Can you fill in the missing values? Can we find a recursive formula? Can we find a general rule, a closed, explicit formula? So one of the things that's different about this than the cookie problem is that the cookie problem, I gave us like 3 examples, and then the first blank was kind of down here in 4. And so we could see that every time I was going down 1, or every time this increased by 1, I could see what the increase was here. One of the things that makes this tricky is that I didn't give you any consecutive numbers. You know what happens at 2 hours and you know what happens at 5 hours, and we actually have to use those to figure this out. So one of the things I know is that if I go from 2 hours to 5 hours, I know that the amount of money that is increased is $18. So from $13.50 to $31.50, that's an increase of $18. Now, one of the things I know is that this change, whatever it is going up down here, is going to be constant. So whatever the difference is between $13.50 and this blank, and this first blank and this second blank, and this second blank and $31.50, those changes all have to be the same. That means that this $18 actually has to be spread across 3 hours of rental. Similarly, if I look at the change from $31.50 to $61.50, I can see that this price went up $30 at the same time that the number of hours went up 5 hours. So this $30 has to be shared equally among those 5 hours. And if I think about 18 shared among 3 people, or 18 divided by 3, that gives me 6. And if I do $30 across 5 hours, that also gives me 6 for every hour, because every change here has to be the same. What I've done here is realize that every time I go down 1, every time the hour increases by 1, the cost is going to increase by $6. And now that I know that, I can go ahead and put these numbers in and think a little bit about this closed formula. Because this is 6, these changes every time something, the hour increases by 1, the cost increases by 6. Again, if I back up to no hours, and I subtract 6, I can see that even if I don't rent the boat, I've got to pay for the life vest, right? Even before I even start. Before I've spent any time on the boat, the first thing I have to do is pay that life vest. Now, that's a one-time cost. So even when you haven't rented any hours in the boat, you're still paying $1.50, and then every hour that you spend in the boat, right, is 6 hours. So it makes sense that I start with $1.50 and then I go up by $6 every time. And if I think about what that means algebraically, that means, hey, you pay $1.50, and then N is the number of hours, and every hour that you're in that boat, you're going to pay another $6. So for example, if I wanted to know how much I would pay for 8 hours on that paddle boat, it's 6 times 8, which is 48, plus another $1.50. So hopefully you were able to use these relationships, and this is something we're going to do a lot in this class, where I'll show you one example and then I'm going to show you a twist on that example. So we're not just blindly trying to memorize steps, but I want you guys to think about what these things mean. These growing patterns where there's a constant change in between those first order differences, like we talked about, the constant change means it changes by the same amount every time you increase by the same amount. Now, whether that's 1 hour, or again, if I went from 2 to 4, that increases 2 hours, but the cost increases $12. So again, that's still $12 over 2 hours, which still is 6 for everyone. Okay, what I want to do now is look across these 4 tasks and see if we can find a big generalization that can help us write closed formulas for these types of growing problems, what we're going to call arithmetic sequences. Each of these previous pattern problems are of a specific type. They're namely called arithmetic sequences. In each case, there is a constant change visible as the values of n increase by 1, and in each case, the change is the adding of an amount. even though these examples, the number increased by a value, it could actually decrease by a value as well. What we want to do now is gather our data from these 4 problems and look across it for patterns and try to make big generalizations on the general form for all arithmetic sequences. So we're going to look at the relationship between the recursive patterns we saw and the closed explicit formulas we saw for each problem. So to begin, here is all the data. Right here is the 1 through 10 for the stickers with rod length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, along with our closed formula. Here is the data for trapezoid tables for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tables, the number of seats, and then our closed formula. Here is the data for the number of boxes of cookies and how much they cost. And we can see that data for 1 through 10 in our closed formula of 3n, or 3n plus 0 if we would. And then the last one here is the number of hours of the boat rental and then how much it costs, the one we just talked about. Here's our data all the way through 10. Here's our closed formula. So what I want to do now is remind us of the constant change for each of these tasks. Remember, if you would here, that every time the number of cubes went up 1, there was a change of positive 4 plus 4 between the number of stickers. Every time the number of tables went up 1, the number of seats increased by 3. Every time the number of boxes of cookies increased by 1, the amount increased by $3. And every time the number of hours increased by 1, the cost of the boat rental was increasing by 6. So I want you to think about the patterns between the recursive, if you notice anything about the recursive numbers that we see here, and how they may relate to the closed formulas, the explicit formulas that we see here. One of the things I hope you notice is that there is a definite relationship between the recursive pattern and the constant change and the coefficient, that number multiplied by the variable, in each of our explicit formulas. So when the constant change was 4, it was 4 multiplied by n. When the constant change was 3, it was 3 multiplied by n. When this constant change was also 3, it was also 3 multiplied by n. And when the constant change was 6, it was 6 multiplied by n. So the first thing that we should notice is that whatever that constant change is going to be the coefficient multiplied by our variable in our explicit form. That's really handy to know. So once I see it's plus 6, when I think about what the closed formula is, that, well, whatever I do to 7, I know I'm going to multiply it by 6. That's 42. What do I have left over? Oh, another $1.50. So after I multiply it by 6, I have to add $1.50. If I'm going to multiply by 3, 6 times 3 is 18. Do I have to add or subtract anything to this to make it 18? Nope, it's already 18. That tells me there's nothing here to add or subtract. Similarly, if I know my constant change is 3, 9 times 3 is 27, but I want it to be 29. Well, that means I better add 2 at the end. There's that constant change. Here's the amount that we add. Same thing here. If it was 4 times 4 is 16, but I want it to be 18, I know I'm going to have to add 2. You may also recall that these numbers are also the values that we found when the input value, the rod length or the number of tables or the number of boxes or the number of hours, was 0. So when there were no rods, there were still, if I followed my pattern, I'd still have 2 stickers. If there was no tables, I'd still have 2 seats, the front and the back. If I had no boxes, I would pay no money. If I had no hours, I'd still have to pay $1.50. That's that life jacket rental. So, in our examples, the closed formulas were all of the form A, some number times n, plus b, where a represented our constant change that we saw in our recursive patterns, and b was the value when n was 0. And again, this should seem familiar. because what we're talking about here are linear relationships. Arithmetic sequences are additive and therefore they are linear in nature, like y equals mx plus b. So this y equals an plus b and y equals mx plus b, where m is the slope, which by the way is the constant change, and b is the y-intercept, the value of the function when x is 0. So what we've just looked at here is, again, these are algebraic ideas, but I think you'll agree when we look back at some of these problems, right? If I think about even trapezoid tables, I can do this problem with third graders and fourth graders. They can count, they can build the tables, they can tell me how many seats there are. They can make the table, they can realize that recursive element. Now, they may not be able to take it all the way to 3n plus 2 and be able to connect it by every table there's 3 seats and then one on the front and one on the back. They may not be able to do that. But you can see how we can start to develop algebraic ideas even within these growing patterns in the elementary grades. So the next thing we're going to do is turn our attention to some other problem solving strategies that go beyond growing patterns, these arithmetic sequences. We're going to look at some other types of problem solving ideas here in our next lecture. Thanks.